Hello everybody, just want to pop on, say hello before I start the lecture. So I'm recording this on an iPad in my bedroom office. There's my little office corner. Yeah, would much rather be with all of you in a classroom. Anyway, in today's lesson I'm going to give you a few definitions. We'll define hydrology and water resources. Then we will derive the conservation of mass equation, and I'll end by introducing the water cycle. I promise these videos will improve over time, so hang in there with me this quarter and let me know if you have any suggestions for improving them. All right, enjoy. So I'm going to start by defining for you hydrology, and hydrology is a science. It's a science that studies the occurrence and movement of water in the environment. Now we're going to define water resource engineering. So water resource engineering is the engineering that deals directly with the science of hydrology. And what it's an engineering that designs systems that match water supply with water demands and designs systems that control, utilize, and manage water. And so what that means is that water resource engineers make sure that everybody who needs it has enough water when they need it, and that when it rains and snows or the snow melts, that the water that is produced does not damage infrastructure and property. When we talk about water resource engineering, we really just consider the following 4 questions. So we ask how much water is needed, how much water is available in any particular area, how are those demands for the water that's needed going to be satisfied, and how is excess water handled. So we're going to come back to these 4 questions again and again this quarter. And I want you to just keep remembering what defines water resource engineering and how it's different than hydrology. So really, if you think about those questions and what water resource engineering is, you'll notice that it really does have to do with the conservation of mass, where the mass that we're talking about is water. So conservation of mass, I know you have studied many times in many different classes, and you'll probably even study it in the context of environmental engineering this quarter as well. So we really are looking at some particular control volume and seeing how much water is coming in and how much water is going out, right? And then that difference between how much water is coming in and how much water is going out is going to change the accumulation or the storage within the system. So in some control volumes, we might be gaining storage, and in some control volumes, we might lose storage. Okay, so we're going to derive here the conservation of mass equation for an incompressible fluid, which if you all took 141 last quarter, you might remember some of those definitions. But the incompressible fluid is basically a fluid that has constant density, and we are going to look at a fluid flow through some fixed region, some control volume in space. And so our biggest job is really going to be to pick that control volume for every problem that we do. So I'm going to go ahead and try to derive here the conservation of mass equation for some given control volume. Okay, so I'm going to start by drawing a control volume. I'll go ahead and draw it in blue box here. It's not the right pen I want. Here we go. Let's try this one. So here's my control volume. Okay. I'm going to summarize or write that as control volume. And it has some inflow, which we'll call I, which is a function of time. Okay, so if you think back to where you have done fluids so far, like a pipe flow, your inflow would be stream flow, right, or flow in a pipe. And you're going to have some outflow, and we'll call that Q. And then inside this control volume, you're going to have storage, and that is also going to be a function of time. Okay, so we're going to write what happens in time to the change in storage. So I'm going to write what happens to the storage over time. So at some future time, t equals delta t, the storage accumulation is going to be equal to the storage right now, plus how much flow comes in, so I'm going to represent that as I of t times delta t, minus how much flow goes out, so minus q of t times delta t. And if we take a quick look here at the units of this, we will see that we're dealing with storage, right? So we have the cubic feet as storage, and our inflows times our time also gives us cubic feet, or a volume, for our storage. So we're going to look at what happens if we allow delta t to be really small here. So as delta t approaches 0, we're going to turn this into more of like a differential equation. So the change in storage with time, the s of t equals delta t minus s of t, is going to be your inflow minus your outflow, right? So this is an important equation. This is really our conservation of mass. And so this I is going to be all of the inflows that occur into the control volume, okay? This I, again, is all the inflows. So we have to think about all the different inflows that are happening in the into the control volume, and then O is all the outflow. So our job as water resource engineers is really to figure out all the outflows and all the inflows into our control volume, and then look at it over some time period. So the big part of water resources here that we really need to pay attention to as water resource engineers is going to be clearly identifying all of these things that I just talked about when I derived that equation. Okay, so the big part of water resources is to identify or pick our control volume. That's really important. And then we need to identify or pick all of the inflows coming into that control volume, so all the places water is entering that control volume, and then likewise identify all the outflow. So we're going to take a look here at some different control volumes that we might be talking about in this class. So let's start small here and get bigger. So first I'm going to think about Heafy-Bergen as a control volume. And that may not be obvious to you because in fluids and environmental engineering, your control volumes are going to be really small. On the other hand, our control volumes in water resources are going to get pretty big. So a volume of a building is actually pretty small in the world of water resources. So when we think about Heafy-Bergen as a control volume, what we might be thinking about here is, let's say that a rainstorm occurs, right? So it rains on top of Heafy-Bergen, and our job here as water resources is to figure out where does that water go. So we could look at the roof as the control volume, being able to predict how much rain might come and where that rain is going to go. As another example, we could zoom out and we could look at the entire Santa Clara campus as our control volume. So we still have Heafy-Bergen, and that is part of our control volume. And so we still need to consider, if a rainstorm comes across Santa Clara, that part of the control volume. But now we're going to have to also think, is there any rain coming in the streets onto our campus, and where is that going to go? Okay, so we're zooming out here and reconsidering all the inflows and outflows. So let's zoom out even further and let's look at what's called a watershed, which we'll define later. But a watershed could be a control volume. And so we're looking here at the watershed in San Jose, the Guadalupe River watershed. And so when we think about a watershed at this scale, we do still want to consider a time duration of a storm, but we also want to think bigger and think about what happens in the entire water year. All the water coming in, that's going to be rainfall, but it's also going to be water that we import in from other sources. And water going out. And the water going out is now going to be water consumed by the populations that live in this watershed. Okay, we can zoom out even further because this watershed is part of a bigger watershed as part of, well, it's actually not part of, but we do get some of our water from the Bay Delta. So if I zoom out and look at California, you can see that we can consider the entire Bay Delta watershed as a control volume. Okay, so we would want to consider all of the precipitation that falls in this watershed over the course of a year or 5 years or a decade, so that we could manage all the reservoirs, manage all the water, not just for the people, but we're also going to talk and consider wildlife, and industry that requires the water, including ag, and a lot of water these days is going to server farms. So all of that is part of water resource engineering. Okay, so here's a bigger watershed that you can think of as a very large scale. And then I'm going to zoom out one last time and show one larger watershed, which is the Mississippi River watershed. This still just has one outlet, right? We all know that the water flows from the Mississippi River into the Gulf of Mexico, although that's not the only sink of water in this control volume. So evaporation, we'll talk about all that later. But this is another example of a control volume. So the entire Earth could be a control volume as another example. Okay, so these are all the types of things that we are going to be considering and talking about this quarter, is picking the control volume that we're interested in order to do the design that we're talking about. And then we'll carefully identify all the inputs and outputs into that control volume. And when we talk about inputs and outputs, really what we're going to talk about can all be seen and discussed by looking at the water cycle, the hydrologic cycle. So I know we've all learned and talked about the water cycle since we were kids, and I know that because my kindergartner can sing you a song about the water cycle. So we are going to study this water cycle in extreme detail this quarter. Okay, so we are going to look at lots of different parts of this water cycle. I'm going to keep bringing this image back over and over through the quarter and talking about really two main parts of this water cycle. And the two main things that we're going to be looking at are the reservoirs, meaning where water is stored. Okay, where is water stored? And we'll talk about that in a second. And you'll see this on this particular water cycle, is it's all the boxes. And then the second thing is all the fluxes, all the ways that water is transferred from one of these reservoirs to another. And so our job this quarter is going to be studying in detail, first, all these fluxes. So we're going to look really closely at what precipitation means, how it occurs, why it occurs, and then study how to use historic records to predict into the future. We're going to look really closely at evaporation and the dynamics behind how that occurs. We're going to look at infiltration, trying to estimate for each rainstorm how much water is going to actually infiltrate into the ground versus run off and hit our rivers and streams. And a big part of this is going to be investigation into figuring out how humans have interfered with this global water cycle, or with the water cycle even at the level of California or Santa Clara, and how we as engineers can work to maintain the global water cycle, keep it sustainable for future. So as we get more droughts or more floods, how we can use engineering and science, hydrology and water resource engineering, to make sure that everyone stays safe. Okay, so that's the end of my first video lecture. Hopefully it went okay. Please give me any feedback, and this is going to be a constantly evolving practice for all of us this quarter. Thank you.